So yeah, so let me just I guess write down the title. So the title of my talk is to talk about these branch regularity theorems in certain stable cases in codimension. Branch regularity results for, say, stable hypersurfaces. And more specifically, this sort of there's a non-flat case which occurs at half integer density, and so that'll sort of be the focus for the talk. So, cool. So I think it makes sense to sort of start with a bit of just background, so why this question comes up. So the sort of story so far, or a subset of the story at least, is that whenever you've got searching for objects which minimize area, at least locally, is a very classical problem. And the regularity theory for things that locally minimize area is now pretty strong. So this started for codimension 1, area minimizers. So for area minimizers, in codimension 1, we have a very strong regularity theory. So there is strong regularity theory. And it's known that the singular set, so wherever the object is not smoothly embedded, is contained within a set which is initially known to just be codimensions at least. Now we know actually it's even more, it's n-7 rectifiable. Let me just start with the simplest case. So the Hausdorff dimension of the singular set of whatever object we're talking about is at most n-7, where n is the dimension of this object. And this can be proved using nowadays relatively soft arguments based on just analyzing certain tangent cones that arise. Say analyzing tangent cones. And you can rule out that many tangent cones happen in this case. And then there's this dimension reduction argument of Federer, which knocks a dimension down to codimension set. When you move up to,
when you say red about white 7, like is there a heuristic or something?
there is a sort of vague heuristic, but it's maybe not most satisfactory. So like the heuristic is kind of if you take two disks in let's just say Rn+1, and you take the minimizer with that boundary in if they're sufficiently close, then in R3 you get a cathenoid. And as you move up the dimensions, the cathenoid kind of comes closer and closer to itself. So then when you go through 7, it finally intersects itself. That's sort of some intuition as to why in 7 dimensions this occurs. And so yeah, this is sharp. So you do get area minimizers, 7-dimensional area minimizers, which are area minimizers and have points to singular sets. So this sort of singular set is generally unavoidable. You can't avoid it. When you go up from just codimension 1 to arbitrary codimension, the situation changes drastically. So just a note about this. So So for area minimizers in codimension, bigger than 1, the best result currently known, at least, is that the dimension bound on the singular set changes from this n-7 to n-2. So you then have that dimension of the singular set is n-2. And this was initially done by Almgren, and since it's been sort of simplified by Camilla. So and again, this is examples of this are much easier to cook up because any complex analytic variety is an area minimizer, and so you can just write down sort of these very simple, like z squared is w cubed in C cross C. This will be area minimizing, and it's got a branch point at the origin. So something like this is an area minimizer locally and has a branch point at the origin. This has now, when you move away from minimizing and drop that assumption, the situation becomes a lot quite different. And especially, so in this talk, I'm just going to focus on codimension 1.
Just one thing, I can missing something. The thing as dimension, dimension 2, yeah.
Yeah. So if you drop area minimizing, the next sort of natural assumption would be not just a critical point of area, but stable. So second variation is non-negative. So I guess physically that makes sense as well. And in codimension 1, this dimension bound now is known to completely fail without additional assumptions. And in particular, these branch point singularities can occur for stable things. So let's just say, let's now drop area minimizing assumption. And just focus on objects which are one that's stationary for the area functional, so critical point. And there's non-negative second variation. And so by objects, I mean varifolds, or integral varifolds, if we know what these are. But I don't think we'll need too much precision about what we mean by varifold. So, but what is known in this setting is that you can recover all this regularity result for area minimizers is actually a consequence of not the minimizing property, but just the local stability with one other geometric condition. So I should probably specify codimension 1. So the codimension 1 area minimizing actually a consequence of just stability. And in fact, it's even a weaker form of stability. You only actually have to assume stability wherever the object is smoothly embedded. So you don't even have to assume across any singularities. So just stability on the smoothly embedded part, which I call the regular set part. And the absence of that's embarrassing. Absence. No, I can't actually spell it. And the non-existence of certain singularities, which are known as classical singularities. So known as what do I mean by a classical singularity? By this, I just mean it's a singular point where if I look at just on a ball about the point, so if this is my classical singularity, then this is actually going to be, in the varifold language, is a sum over a finite number of smooth hypersurfaces with a boundary in this ball that all meet along the common boundary. So it looks something like this. And these are three, so this is three smoothly embedded sheets, which away from this axis, this common boundary they all have, they don't intersect. And yeah, they only intersect along this common boundary. So these are smooth embedded hypersurfaces. They could coincide entirely, but if they don't, then they're separate. Smoothly embedded hypersurfaces with boundary. Which meet only at the boundary. So if you don't have these singularities, which for area minimizers in codimension 1 is very easy to rule out. You can just, if you take a tangent plane at the point, you'd have a union of half planes or half hyperplanes that meet along an axis, and it's very simple to do like one-dimensional area comparison arguments to say that this can't happen. They can't be minimizing unless it's a plane. And so what was proved in this setting is, this was by Neshan Wickramasekera. Is that if you have one of these, also if V is one of these objects, so it's a stationary integral varifold, and it's stable on its smoothly embedded part, so on the regular part, and V has no classical singularities, then in fact this conclusion still holds. So you still have this codimension 7 singular set bound. And so in particular, this tells you something about the class, like it tells you various compactness results for things which are stable and smoothly embedded. If I had a sequence of smoothly embedded without any singularities, well, I think we've had this more, I should say. Like there are, this is true plus some other regularity theorems which are very important. And those regularity theorems rule out things like branch points from occurring in the set. And so what you get from this as a consequence is you get some compactness theory for smoothly embedded. Hypersurfaces, stable hypersurfaces. So if you're in low dimensions where you don't have singular sets, then you actually know that your limit will also be smoothly embedded and things like that. And a very natural question that arises from all of this is, well, okay, what about, is there a compactness theory for not smoothly embedded stable hypersurfaces, but smoothly immersed? So a natural question what about smoothly immersed? And some things are known in low dimensions. This was the work of Shane Simon Yao and Shane Simon. They proved curvature estimates in sort of not all of the regular dimensions, but only up to dimension like 5-dimensional objects in R6. And S6 is still open as far as I'm aware. And so to deal with this problem, you somehow need to develop a regularity theory where you allow for these classical singularities. If you're immersed, you're going to have crossings, and when you cross, maybe some bad things can happen. And the point is that this result also tells you, like, there's stuff in this part which I'm not explaining, but this also tells you that if you have these very bad branch points, like we had in this higher codimension setting, then the branch points have to be limits of classical singularities. Any branch point has to be locally a limit of crossings. So if you want to understand sort of singularities of immersed, smoothly immersed hypersurfaces, or at least limits of them, so how the singularities could degenerate, you need to understand what happens at, say, one of these branch points, which, like I say, can occur. There are known examples of stable hypersurfaces which have branch points. And one of the sort of drawbacks of, well, a significant drawback of when a branch set is possible is that the sort of set of these branch points is like the worst, and sometimes the worst type of singularity you could have. And it's not even known if the sort of branch points could have positive measure in the variable. And this is like a significant open question. So a big problem is limits could develop branch points And in particular, like this could be a very large set. So this could be a priori B, very large set. And so, I mean, this is one of the significant like changes between in the area minimizing setting between this and this result, because in high codimension branch points can occur, and then the theory is like you need very strong arguments, and this is what Almgren did for his 1,000 pages book. Like this is, he basically had to deal with these branch points. So so what you want to do is somehow understand or prove regularity results in the stable setting when classical singularities occur. So we want to prove stable hypersurface setting when classical singularities occur. And Neshan proved some results under the assumption of like if you already assume that the singular set was essentially codimension 2 away from the branch that was codimension 2, then you could prove some things. But then last year we took this further and we were able to prove a result which gave a regularity theorem in a certain case. So let me just write this. So what we're able to do is, so this was 21. So, okay, I'm not going to be able to fit it. Okay, I'll come over here. So what we're going to prove is that if you fix integer q, that's at least 2. So this is kind of the branching order, if you will. Every branch point is essentially a branching of a certain integer number of sheets that interacts in some way. It's a multiplicity, if you will. So you fix it into q, and the result says that there exists an epsilon, which only depends on the dimension of q, such that if you have any one of these varifolds, so if V is stationary into a varifold, it's stable on its embedded part. And instead of ruling out every classical singularity like we did here, like Neshan did here, if I just rule out crossings of less than q sheets, so I rule out classical singularities formed of less than, if you count these as half sheets, then I want to rule out less than 2q.
Just one question. What's the codimension here?
This is codimension 1. yeah, this is everything now as a resolution. So if you rule out classical singularities formed of, so this is morally Q hypersurfaces, but if you count them with boundary, so it's 2Q. So 2Q half submanifolds with boundary, sorry. Then if this V is at a branch point, if you're at a branch point in V, this means that you can show that this means that you're very close to a plane, a hyperplane of density Q in that setting. Then if V is epsilon close as a varifold, again, I'm being slightly vague as what I mean by this. If you're close in the varifold topology, like as a measure, then, so if you're epsilon close to a hyperplane P with multiplicity Q, so V looks like Q sheets as well, then actually this V is locally going to be essentially a C1-alpha graph of the plane in a suitable sense. So I'll say that then V is it's slightly more complicated. It's a generalized C1-alpha multi-valued graph. I'll say what I mean by this in a second. Graph over a subset of P. So again, this is imprecise because it should be restricting to certain sets, but like morally, once you're close to a multiplicity Q plane, if you're ruling out classical singularities formed of less than 2 Q sheets, then I actually have this sort of graph structure and the situation is better understood. So maybe it's just a special case is informative. So like in the case Q is 2, we're basically saying that if you rule out classical singularities of density formed of less than 4, so the only case you can have is actually 3. So if you rule out a picture like this, you have 3 things coming together, then near a plane of multiplicity 2, V is actually going to be locally a graph, which above every point on the plane takes 2 values in some sort of unordered sense. So it's not, it doesn't split up into 2 separate functions, but they're sort of mixed in some way.
So in particular, you would conclude that the points in which these graphs come together, they all have to come together, right?
Yeah, exactly. Yeah. So this is
so like there's not going to be, say, a place in which 2 of them intersect, but the others don't. Like
no, exactly.
all of them
They all have to come together at the same point.
And the subset of P is pretty large.
Yeah, I mean, yeah, you would quantify if I'm close on say a unit ball than a graphic graph.
Yeah, so the subset is a regular subset. I mean, it's not.
Yeah, it's it's not some funky. Yeah, it's like, yeah. So V would be a 2-valued graph.
Is that the reason why you're all together? It's because it's essentially like a Q root of something. Or...
You mean like why all the sheets?
Yeah, why somehow all of them, if they come together, they come together. All of them.
Oh, so it's going to, I mean, this isn't something that's forced because of the assumption. Like if you allow, like, if you remove this assumption, then you'd expect fewer sheets to come together at points. But just because you're forcing this.
Okay, you're forcing this. So somehow what you're saying is that if I'm forcing that, I can't come together in a weird way.
Yeah, it has to, exactly.
Okay.
It has to all come together at once.
I can't come together like, on a fractal or something like that.
Yeah.
Okay. Good. But otherwise, you could, I guess, make examples in which self-intersections are kind of.
Well, so the thing is that there are two ways. So this, if I just quickly say, actually, no, yeah. So there are two ways that this can come together. One is at a classical singularity. That's a nice intersection. You understand that that's actually, in this case, it'll be very smooth. They'll be smoothly embedded, coming along a smooth axis. But the branch set, when they actually come together in like a branched way, all we're saying is that there is some sort of C1-alpha structure. Like the tangent plane varies in a C1-alpha way, essentially. So you have unique tangent planes at every point.
So they could actually come together, but
so the branch, there's nothing.
So there might be branching outside of this singular point. Okay.
Yeah, and in particular, there's nothing being said about the size of the branch set current. So this still could have a branch set which is very large, positive measure, things like this. So the structure, the structure of the branch set itself is still open. That's something that we're working on. So we expect that you should also be able to prove that it's codimension 2 and rectifiable and things like this, hopefully, in the end. Certainly, so in the Q is 2 case, this is already known. So when Q is 2 and you're just ruling out this, and in this case, actually, the situation is somewhat simpler, and you have this sort of generalized C1-alpha, which I haven't quite defined yet, is actually just classically a C1-alpha multi-valued function. So it's actually a 2-valued function. So when Q is 2, you actually get that over the multiplicity 2 plane. It's a 2-valued C1-alpha function. And we know Leon and Neshan proved first that it's codimension 2, and more recently, Neshan and Brian Kroll proved that it's also a -2 rectifier. So in this case, you actually know that the branch set is countably a -2 rectifier.
Just clarify. You mean that the 2-variable plane is Veblen?
Yeah, exactly. And just to say what this generalized C1-alpha means, so when you're talking about multi-valued functions, they can cross. This is the whole point. And the thing is that a C1-alpha crossing would typically look like, let's just say it looks something like this, where each you have, it's all C1-alpha, like at a classical singularity. However, when you're just working with varifolds, a classical singularity doesn't need to be inversed. So you could have a classical singularity that looks something like, should say something that looks like this, and we'll put something like that. And this is not an immersed classical singularity, but you still actually have that each of these sheets is a C1-alpha, in fact, smooth submanifold with boundary in this case. So the generalized just refers to that classical crossings, classical singularities they don't need to be immersed. But you still have some regularity there of each of the different sheets. So this is good. It says in some sense that, maybe I should think about that more. I think it does say something about you can't get certain branch points in certain limits of smoothly immersed things. But the next question, the next natural question from this is, well, can you go further, basically? Like, I'm ruling out, so in this Q is 2 case, I rule out these triple junctions, as I said, and I can understand density 2 branch points or near multiplicity 2 planes. Could I also say something about multiplicity 3 plane or density 3 branch point? That seems to be a hard question. However, sort of an intermediate step towards this would be to go in the middle. So you want to, let's just look at that case. So would like to go from multiplicity 2 hyperplane to multiplicity 3 hyperplane. This seems hard. At least I don't know how to do it. But an intermediate step would be to try and understand the structure in between these two, which would be that when you're close to a picture like this, where you're fond of 2q plus 1 different half hyperplanes. So you're ruling out classical singularities of less than 2q. In some sense, this result tells you can understand when it's exactly equal to 2q. There are other results here about regularity results near classical singularities of 2q half hyperplanes. So I'm breezing over. This is like the hardest case, if you will, of 2q half hyperplanes. So you could ask, well, can you say anything about the case where you're close to a union of 2q plus 1 half hyperplanes? That's like the next case. So an intermediate question. What about when V is close to 2q plus 1 half hyperplanes? Anything along that axis? So maybe just to make this clearer, in case it's not clear what I mean. Like in the Q2 case, you rule out this, and then I claim that this result with Neshan, you can understand pictures like this, where it's 4, and the most degenerate situation you could have is when these 4 half hyperplanes collapse into 1 multiplicity 2 hyperplane itself. Like, so this result here understands all of these situations. You would like to be able to say something about this picture, or sort of even sort of weaker, something where you've got like, say, just three hyperplanes like this. This also seems hard. So let's just go in the middle where we forget about one of these. And can we say something? So it's like in the middle between 2 and 3. And these pictures can occur. This is a classical singularity in some sense. It's just not immersed. It won't be immersed. So you want to understand that intermediate case. So, this is possible, it turns out. And so this is what. So I did this in the case Q2, also part of my thesis. That was 2021. And then in general case, this was this year. And it basically says that this is possible. So that if you fix such a cone, so fix a C, which is a sum of 2q plus 1 half hyperplanes of the common boundary. Then there is an epsilon, which only depends on the dimension of this cone. In fact, it just depends on the angle between the smallest angle between the half hyperplanes. Such that if you have all the same assumptions, so the stationary interval, it's stable on its regular part, and you rule out classical singularities of this form, so less than 2q, such that for V under the same assumptions, if V is epsilon close to C, as in this varifold topology, then in fact V is a generalized C1-alpha multi-value prime over C. And again, not being too precise exactly what I mean by over C. Yeah, it's one of those things that it's like on a half, if it's close on a unit ball, then it's a graph over a half ball, but you have to be slightly careful about where your graphs are defined on the half hyperplanes. And so in particular, the set of points where the density is equal to q plus a half in V is actually a smooth, it's a C1-alpha submanifold. Usual sense. So all the q points where the sheets meet, they do meet on a C1-alpha submanifold.
So here you're again asking to not have classical singularity.
Yeah, but it's still the same.
Yeah.
It's still less than 2q. It's not like I'm still allowing q crossings. And so in particular, you can still have, so there's a sort of an open question from this. And if I look at just the simplest case, when q is 2, so you're looking at a picture like, say like this. And so the result says that essentially in this case, I would look like some sort of C1-alpha perturbation of this. In cases where you have that these half hyperplanes actually occur at multiplicity, so you could have branch points which limit onto the spine. This is unclear if this is actually possible or not. It might turn out that this is not possible. If you could rule this out, then the proof does become drastically simpler. And one of the difficulties of the proof is this possibility that you could have these branch points that can generate to the spine, essentially. So, are there any questions so far?
So in all the cases in which the multiplicity is exactly 1, you actually get that it's just classical sheets coming together.
Yeah, in that case, it's going to be a classical singularity, yeah, like in the usual sense, yeah. But when you have higher multiplicity, it could be actually, yeah. Okay. So in the last 15 minutes, I wanted to talk about some aspects of how this is proved and like the difference between q is 2 to q at least 3. So there are numerous aspects which are similar in the proofs, but there's a couple which are quite different. And it's all to do with basically when q is 2, as I said over here, you have a much better understanding of the branch. And in particular, you have this dimension bound. You know, the branch has codimension 2. And that drastically helps. So one of the sort of key difference between the Q is 2 case and at least 3 is that the fact that you can still prove this result in a setting where the branch set could be very, very large. And so, you know, these, if I were to draw a two-dimensional picture, it's a triple junction, but let's put these as multiplicity 2. You know, I could have branch points that are like all along here. Okay, of course they can't be lines like this, but like, well, I could say maybe they could. I guess maybe a priori could. And this is like a very bad picture. So there are some nice aspects of that in the general case, which I wanted to talk about. So the first sort of problem, well, one of the key problems that always arises in these problems is to understand these so-called gap regions. So one key problem is understanding gap regions. And a gap region is when you're close to a picture like this, or let's just say this one, but I don't actually have any point where I look like this. So I don't actually have, in this setting, any points of density 5 halves. So we're five half hyperplanes or half submanifolds of boundary put together. So this is a region where B is close to C, but B does not have the same symmetries as C, essentially. And so like a very basic picture you could draw like this is in this case, with the 5 halves case, if you had a picture like this, you could have something close by that looks like this. So now I've got no point here where I look like 5 submanifolds with boundary joining at a point. But the observation is that if this happens, I should actually get something of a lower number of crossings, which I'm ruling out. So that's promising. That's promising that actually maybe something you could be able to prove that this doesn't occur. Yeah, it's a very simplified picture, but but it turns out that you can actually argue that, so that this can't happen. Let's sort of see why you might expect this to not happen. So in a gap region, this is sort of what it means precisely is that you have this sort of density function which measures how many sheets you've got. And this density function is always less than the density of if you had exactly 2q plus 1, I mean, maybe it's more informative to write it as this. Each of your submanifolds contributes half the density because it's got a boundary, so you're cutting it in half. in such a region, you actually understand the singular set quite well, because it turns out up to a set of codimension 2, a closed set in fact, in fact, there's even countably a -2 rectifiable from neighborhood torch, but that's not necessary. So up to a sort of a small set, every other point is either a smoothly embedded point or it's a classical singularity, like a smoothly embedded thing where Q sheets come together. So it's a classical singularity where 2 Q sheets come together. I mean, why is this? Well, this assumption means you can't have more than 2 Q coming together. And our initial assumption is that we don't have less than 2 Q. So if you have any, it's exactly 2 Q. Or you can have this branch set where locally this other regularity result holds on this board, where you know it's a C1-alpha multi-valued function. So in particular, this gives you that the topologically, this is quite a simple picture because it's a graph. It's a union of Lipschitz graphs. So you can't have a picture like, a very bad picture would be if I had sort of a sequence of necks that get smaller and smaller, and degenerate to a point and the same on the other side. And so this result rules out this very bad picture. So the point is away from quite a small set, you actually have quite a good understanding of what's happening. And so this is one of the differences between Q is 2 and least Q, is that when Q is 2, I know this is also codimension 2. So I can just chuck this in here. And like I said, I mean, we conjecture that you can, well, we're trying to prove that this is codimension 2 anyway, but still it's interesting that you can do it without that assumption. So what this enables you to do is you can essentially restrict yourself to a setting where you avoid this bad set. It's closed codimension 2. So essentially you can take, if I'll draw another picture, if this is my cone, this is an n-1 dimensional axis. And this says codimension 2. So I know that almost every slice I take perpendicular to that axis, that's like this. Almost every slice is going to avoid that bad set. That bad set's also closed. So if I'm avoiding it, I can actually get like a little wedge region, where I know that in this wedge region, I'm avoiding it. So I know in this red wedge, every point is smoothly embedded, or it's a classical singularity, or it's the branch point, which has got this nice sort of Lipschitz graph structure, if you will. Now, there are other arguments sort of similar arguments in literature to sort of deal with this, but not when you have this big branch set. And in that case, like if you know, for example, if you know that the branch set is already codimension 2, and you can avoid this branch set in this wedge as well, if you just had smoothly embedded points, well, this picture would be impossible. I've got 3 half hyperplanes. It's smoothly embedded. I can't have say an odd number of boundary components for a smoothly embedded thing. If I have classical singularities, where it is just an even number of sheets coming together, this also shouldn't be a problem, because fine, I can have crossings, but there's always an even number of crossings, and so I can't change the number of boundary components. And so the number of boundary components is odd, then this picture should also be bad. I shouldn't be able to have this. So that's essentially how the argument goes when you know the branch set is small anyway. But if you have a large branch set, I can't avoid this. How would you argue? And the same idea essentially it feels like it should work, because at a branch point, well, with this regularity theorem, I know it's at least like a union of Lipschitz, like an even or an integer number of Lipschitz graphs. And so the number of boundary components should change. So how can you argue that this is also still a bad picture? And so the usual arguments would have used like a Sard's theorem type argument to find like a slice where everything's smoothly embedded. You take a two-dimensional slice perpendicular to the n-1 dimensional axis. Everything's smoothly embedded, and then you can argue that one-dimensional smoothly embedded thing, even number of boundary components, contradiction. But how can you find a good slice when your branch set is large? And so it turns out that you don't want to think of it as a slice, but instead think of it as like, I just want to put like a two-dimensional disk. If I can put a disk in this wedge region that intersects everything transversely, I can pull back to the disk. It's a two-dimensional disk. I have a one-dimensional thing inside, odd number of boundary components. I understand the structure locally about each point in the disk, because it's either it's either like a one-dimensional thing. So you have an odd number of things on the boundary, and every point in here is either going to be an embedded point, so it looks like this, or you're going to have a point where an even number of things come together, or you've got this problematic branch set where they could all join, and the point is that that set could also still be large. But it shouldn't matter too much. So provided you can get this nice disk, you can essentially do it like an argument where you unravel the curves one by one and count the boundary components, and argue that actually, even in this branched case, provided I can find this sort of nice disk where it's intersecting the branch set transversely, then I can pull back to the disk and I can unravel the curves and count the boundary components that are contradiction. And the only issue with finding this disk is that the branch set is only C1-alpha regular initially. And so Sard's theorem is you need to be a bit careful with it. But there are sort of sufficiently weak versions of Sard's theorem that you can apply in order to take a slice and perturb it to a nice slice where you do intersect the branch set transversely, and then pull back to the disk in order to conclude that this picture can't happen. So that's like a very rough way of how you can argue that these gap regions don't occur. And I'm aware of the time. Once you've got that these gap regions don't occur, you're in a much nicer set, basically. it's still not clear what happens because the next significant difficulty is there's this sort of standard, I won't say standard, but sort of now relatively standard linearization arguments where I take a sequence of things, I find graph structures over subsets of the cone and I linearize them. And the problem is that when you linearize, you end up with multi-valued functions on a half plane or half hyperplane, and you want to understand the boundary regularity, but multi-valued functions aren't like single-valued functions, and there isn't, as far as I'm aware, at least, a boundary regularity theory for multi-valued functions. And so you have to, there's a whole other sort of geometric analytical argument to deal with this, which involves these things called a fine block procedure, and then you have to do an additional thing called an ultra fine block procedure. It's somewhat involved. I don't have to talk about this. Yeah, okay, I think that makes sense.
Questions? So, what is the information that you have on these sheets that you get from the linearization at the somehow when they come close to the say to the
in the
spine,
final result or like in the proof, like how
in the proof, right? So okay, so so once you don't have the gap region, you will have the hard-Simon inequality.
Yeah.
Right, and it's telling you that they all come together, like even if they are multigraphs, but they are still kind of going to stick together.
So you get that even if they're multigraphs, the values of each multigraph at the boundary. So if you had a multiplicity 2, let's just say, half plane, when I linearize, I know that both values, whatever they are, at the boundary, they're going to be the same.
They're just going to be the same.
Yeah, and this is basically what ends up ruling out this feature. Because they're the same, I can't split. Basically, I can't split the spine up into smaller things. So yeah, like hard-Simon is what gives you that in the end. Once you've got the C1-alpha boundary regularity, you know that when you perturb to a new code, you still know that it's going to be of the form 5 half planes together.
But so the C1, I mean, like the boundary regularity you want it for multifunctions who actually have like a collapsed.
Yeah, exactly.
At the boundary.
Yeah.
So then, I mean, at the boundary, it's a single function, and now you would actually like to say that is better.
So the function of the boundary, you can.
That is probably okay because of some averaging procedure. So yeah, then you want to subtract that, and so essentially your boundary regularity is going to be for something which is equal to.
Yeah, symmetric. Yeah, exactly. You want to prove in the end you have a symmetric function which has, that's like a rough picture, I guess. Like it's symmetric about the half plane, and you want to prove that each. But yeah, it could be more than one value. I get that. It doesn't have to be 2. But yeah, like each of those values on the symmetric part C1-alpha. Are you like taking a symmetrization on the other side to just study when you mean?
Yeah, because I mean, like it would be tempting to do that, no? Maybe like, you do that, and then you have a.
So yeah, you can. So you would like to reflect,
yes,
and think of it as over a whole plane. You can do this, but the thing is that you first need to actually be able to say anything nice about the reflection. I do need to know some sort of. I would like to know some sort of at least C1 regularity, like joining the sheet. So the argument is like this, where you basically bootstrap the C1 regularity. Like, so you first start with looking at just homogeneous degree 1
Mhm.
blow-ups, and they have a spine still, like in the subspace of the joining.
Mhm.
And you can prove that away from that spine, they are C1-alpha. Okay, if the spine's already n-1 dimensional, you're done because that's everything. So that's a good case. So you know it's dimension at least at most n-2. And so you get it C1-alpha away from the spine, and then this is, so you can reflect, and you know that you're going to be C1-alpha across the boundary when you reflect away from this n-2 dimensional.
Okay, so which is like some set in which you don't have a nice blow up.
Yeah,
Okay.
yeah. And so to get over this, that's one of the difficulties that you have to somehow. So yeah, to be fair, getting the C1 out, the C1 regularity away from that subset is where most of the work comes. If you can prove that, you're in a good case. This is the sort of reverse Hart-Simon style argument, which is and that's why you need these fine and ultra-fine blow-ups, basically, because you do this reverse Hart-Simon argument, and that's, you say either reverse Hart-Simon holds, or I'm actually already C1 regular. And the way you get that dichotomy is using the fact that you already understand. It's like an inductive argument. So in the case when Q is 2, you have 3 pictures. You have when everything's multiplicity 1, or you have when one thing has density Q, and you have 3 other ones. And then the final picture is when you have 2 density Q ones. And to prove the regularity of the blobs here, you need to use the regularity so you establish this one first. I say that because this is a nice case, right? If I have no gaps, yeah, so now it's just single valued boundary regularity is easy for the blow up. So I can prove the regularity result here. When I go here, if I want to prove the boundary regularity of the blob on this plane, I have to basically say either the blob, it's like on this half plane, either it splits. And if it splits, then actually my blob looks like this. And so when I blow this back down to the varifold level, I actually look closer to one of these pictures. And then you want to use your regularity theorem from here to say that actually I am already C1-alpha regular. I blow that up, and so my blob was C1 already. And once you've got that you're C1 away from the spine, then you can do this reflection argument. And then you end up basically wanting to prove that you have a frequency function along that whole boundary where you reflect. And it turns out that it's actually quite a nice argument that you can prove that if you're C1 at the boundary, then you can extend the interior frequency function you have here to the boundary point where it's C1. But if you know that it's C1 away from the codimension 2 set, this is a subspace, that's removable from squash and squeeze. So you can actually extend across the whole, like to get frequency multiplicity away across the everything. But you can only do this when you know that you're C1 up to the boundary. And so you can only prove that for homogeneous degree 1 elements first. So it's like to prove the regularity in full for the blobs, you first prove it for homogeneous degree 1 things. But to do that, you have to first prove like a sort of partial regularity result away from the spine of the blow-up, which you do using your inductive like regularity results. And once you've got that, then you can extend frequency to the boundary and classify the homogeneous degree 1 blobs. And once you've classified them, then
But how do you rule out frequencies below 1 at the boundary? Like how? Because we have.
but this is hard.
Okay, so this.
Yeah, well, that's why you need the density gap. Yeah. Like once you've ruled out density gaps, then you know you're not going to have frequency less than 1 at the boundary. And yeah, and the thing is that you already have in the interior, you already have your regularity, like the. So still, yeah, you can use this regularity result to understand so you don't need any approximate graphs or anything, you can just apply this result to understand the blobs in the interior. So it just becomes a boundary problem. And this is what fails completely as soon as you go. Like, if you try to go straight to QS3 with the QS2 result, it's just not going to work.
Okay. Thank you.